All right, so here in this video, we're going to construct new power series from old power series, or from known power series, I should say. So for example, let's say that we had 1 over 1 minus x times x minus 2. All right, and I wanted to find the power series that represents this function. Okay. All right. So as always here, we have our geometric, right? As a reminder here, x to the n. Starting at 0, we have 1 plus x squared, etc. Right, and that's the function 1 over 1 minus x. So looking at that and looking at what I have here, then I see that I can try and do the same thing by probably splitting it up using a partial fraction decomposition. So we get something like this. So again, I'll skip the kind of work of the partial fraction decomposition. And here we'll assume that that's something that you guys are able to work through here, where I covered in a previous section, just so we can jump straight to just identifying the power series here. So that's the partial fraction decomposition, and then when it comes down to here is to kind of match that similar pattern here. That it looks like the first one is good. I don't have much to do there. Now in the bottom part, I'm going to factor out a -2. All right. And the reason for the negative here, all right, so plus, just be careful with my negative signs here. I'll get 1 and then minus x over 2. Okay, all right, and then notice here I'll have -1 times 1 over 1 minus x, and this becomes plus 1/2 times 1 over 1 minus x over 2. Okay. All right, and then here we get -1 sum x to the n plus 1/2 sum x over 2 to the n. All right, and now we have a n is equal to 0, all right, to infinity, n is equal to 0 to infinity. And here, just to kind of reorganize this, here we'll have the sum here, -1 plus 1/2 1 over 2 to the n x to the n. Okay, oops, and then n is equal to 0 to infinity, n is equal to 0 to infinity of -1 plus 1 over 2 to the n plus 1 x to the n. We can write it as one power series here. Okay, so that's what we do when we're trying to construct a power series. Now, sometimes we're asked to determine what function it is, right? So here, for example, the sum n is equal to 0 to infinity of 1 over 3 to the n x to the n. All right, and we're asked to determine here, right, what function does this represent, right? So this looks like whenever we have to the n power, I could write it like this, right? And now through our geometric series, we know this converges to this quantity here. All right, and then here, oops, excuse me, no, and just 1 over x minus 3, right? And multiplying through by 3, we get 3 minus x. And that is the function that that power series represents. All right, let's do one more. All right, one little bit more challenging here. So let's say we had the function, the power series 1 over x minus 3 to the 2n minus 1. And I want to determine which power which function is represented by this series, right? And this starts from n equals 1 to infinity. Okay, so again, I'm trying to kind of work off of this model here, Cn x to the n, right? Just our basic geometric series here. So the first step here is I'm just gonna do some manipulation here. So it looks like it's centered at 3. So n is equal to 1 to infinity, 1 x minus 3 2n, x minus 3 to the negative 1. Okay, so it looks like this using properties of the negative exponents. We get n minus 1 to infinity. We get x minus 3 as in the numerator over x minus 3 squared and 2n. Okay. All right, so we're going to keep moving it along here. Okay, and then noticing this here, we have, I'm going to rewrite this with the x minus 3 on the outside of the sum, since it doesn't depend on n. N is equal to 1 to infinity, and then here we have 1 over x minus 3 squared to the n. Okay, and again, really why I want to write it this way is just kind of pattern matching to our geometric series, right, where we have n, 1 to the n is always 1, and then we multiply the exponent, so that's 2n. All right, now there's one other thing that kind of sticks out here, is that usually our geometric series starts at 0. All right, that first term is always 1. Etc. Now this one doesn't start at 0, it starts at 1. So what's missing is that initial 1, right? So I'm going to add it in, right? But again, as always, mathematicians' favorite trick is adding 0 or multiplying by 1. In this case, I'm going to add 0 by introducing plus 1 minus 1. Now what I'm going to do here is now this part becomes my new series, x minus 3. Now it starts at 0 to infinity of 1 over x minus 3 squared to the n, and then minus 1. I'm going to distribute that x minus 3 minus the quantity x minus 3. Okay, and now keeping it going here, this part is now my geometric, which is just x minus 3 over 1 minus 1 over x minus 3 squared, and then minus the quantity x minus 3. Okay, let me simplify this further. I'm going to get rid of the complex fraction here. So this becomes x minus 3 squared, or actually cubed, over x minus 3 squared minus 1. All right, so again, here I just got rid of the complex fraction by multiplying by the quantity x minus 3 squared. And now minus x minus 3. Okay, so I'm going to rewrite this as just one rational function. So that's x minus 3 squared minus 1, x minus 3 cubed, minus x minus 3 times x minus 3 squared minus 1. All right, multiplication by the common denominator. All right, and now here I'm going to factor out. Again, I never try to expand anything. I really just want to factor and go from there. X minus 3 squared. I factored out this factor of x minus 3, so it's minus x minus 3 squared, and then plus 1 all over x minus 3 squared minus 1. And notice here that these factors go to 0. I'm left with 1. And then I'm left with the quantity x minus 3 over x minus 3 squared minus 1. So that is the function that my original series here represented. Okay, so again, right, kind of as you work through these, always think of how am I going to match that pattern, right? That's kind of how we arrive at our conclusions here.